In October 2023, the concrete-faced rock-filled Teesta 3 Dam in India suffered complete structural failure. The trigger was a glacial lake outburst GRUD. In the steep, orographically controlled catchments of the Himalayas, these high-altitude lakes can breach suddenly, sending massive, debris-laden floodwaves down the valley. Post-event analyses of Teesta 3, Tala, and Malana 2 indicate that the civil structures themselves largely adhered to established engineering safety codes before they were overwhelmed. Structural robustness fails to prevent catastrophe when the gates meant to modulate the flow remain frozen in place during a surge, forcing the reservoir into a state of overtopping. The actual bottleneck in these catastrophic events lies in the hydromechanical, or HM systems, specifically the failure of spillway gates to actuate under load. Traditionally, dam safety audits evaluate these complex mechanisms as binary states, assuming they either work perfectly or they do not. This simplification breaks down in high-stress, compound hazard environments. This equation calculates the probability of hydromechanical loss, replacing the binary checklist with a unified risk model. The total failure probability is driven by 4 variables: mechanical degradation, electrical power loss, control network failure, and human organizational factors. Building true resilience requires moving away from static compliance checks to quantify the dynamic failure pathways across all 4 of these components. We can isolate the mechanical failure variable by looking at the 100-megawatt Malana 2 hydroelectric project in 2023. During an intense monsoon, a flash flood generated sudden inflows heavily loaded with silt, large boulders, and woody debris. This physical load lodged into the gate tracks and gantry hoists, seizing the mechanisms and rendering the spillway entirely inoperable at peak inflow. This chart models time-dependent mechanical reliability, R of T. It serves as the baseline for calculating failure probability. Engineers use an exponential decay curve for random shocks, while relying on a Weibull distribution to map wear-out processes like corrosion or fatigue. The Malana 2 incident demonstrates that Himalayan models must explicitly inject the probability of instantaneous mechanical jamming caused by dynamic, impact-induced debris loads. Accurate mechanical reliability assessment requires calculating immediate survival under extreme physical stress, rather than simply predicting long-term material wear. To isolate the electrical and control system variables, we look to the October 2025 overtopping of the Tala Dam in Ratan. This reliability block diagram maps the electrical paths required to open a single gate. Primary grid power flows through transformers, while emergency diesel generators and SCADA systems operate as backups. At Tala, extreme rainfall triggered a cascading failure. A single upstream power vulnerability severed the actuation logic for multiple independent gates simultaneously. To calculate this risk, analysts use Markov models that account for state-dependent transitions, like the probability of a generator failing to start. Engineering redundant physical spillway bays provides no actual safety if the shared power and control networks linking them represent a single point of failure. We return to the Teesta 3 disaster to examine the human element. Operators faced a massive floodwave surging through a dark mountain gorge. A glacial lake outburst compresses the time for intervention. Operators had mere minutes to interpret the incoming surge and execute a rapid gate sequencing maneuver. Under standard conditions, human reliability analysis shows that the baseline probability for operator error in a control room remains low, but that baseline shifts when subjected to performance-shaping factors. These include severe time pressure, deep physical fatigue, and ambiguous SCADA alarms. This matrix shows how specific performance-shaping factors multiply the baseline error rate by 1 to 2 orders of magnitude. Vague forecasting and high stakes directly induce cognitive overload. When operators are paralyzed by a lack of integrated data, deploying robust manual override mechanisms in total darkness becomes a physical impossibility. The failure of human response is the mathematical result of cognitive overload in a poorly integrated system. With all variables isolated, we can synthesize the final probabilistic risk model. This fault tree analysis begins with mechanical degradation probabilities, mapping material wear and jamming risks. It expands downward to include electrical and control network blackout odds. Finally, we attach human organizational factors. All paths funnel to a singular output, the hydromechanical functional loss probability. The resulting data is stark. Combining an emergency generator failure with operator delay increases the probability of system loss by an entire order of magnitude compared to assessing mechanical failure in isolation. True safety evaluation requires calculating engineering robustness and human cognition as a single interdependent entity. Once the failure pathways are quantified, the model provides a blueprint for targeted engineering mitigations. On the hardware side, this requires upgrading gate seals, trunnion bearings, and guide systems to explicitly tolerate high debris loads and boulder impacts. To protect the control logic, designers must install physically independent, hardwired emergency actuating circuits for every individual gate, completely bypassing central automation networks. To mitigate human error, advanced sensor fusion can integrate live upstream glaciological and hydrometric data directly into the dam's SCADA system. This early warning integration directly addresses the human reliability analysis matrix by lengthening the decision window and reducing cognitive overload under pressure. We cannot remove sudden geological hazards from the Himalayan environment. Instead, we have to engineer adaptive resilience into the operator's response window. Industry standards must move away from deterministic, strictly civil-centric safety audits. A hydroelectric facility operates as a complex socio-technical system. The mechanical hardware limits, the vulnerabilities in the control network, and the constraints of human cognition under stress are inextricably linked. When an extreme event strikes, the survival of downstream populations relies entirely on mastering the complex math of hydromechanical reliability.